constantly updating your credences, just like John Simon said that rational agents should. All right, onwards and upwards. So what I want to talk about today is both the big puzzle of what to make of quantum mechanics, and also connect with some other very pesky questions. There's another debate which has raged on in the physics community for about a century also, namely what to make exactly of the second law of thermodynamics. It's proven to be almost as controversial and certainly as long-lived. And on one hand, you have people like Arthur Eddington, who said here very eloquently that the law that entropy always increases holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There can be nothing in for it but to collapse in deepest humiliation. Thus spake Arthur Eddington. On the other hand, there have been very serious objections raised by other titans like Maxwell, Gibbs, Loschmidt, Poincaré, and more recently both Roger Penrose in fact, at the last workshop I attended in Oxford, and also Sean Carroll, have raised some serious issues to do with cosmology and the so-called cosmological entropy problem. And what I'm going to try to convince you of today is that I think that these two great controversies, in quantum mechanics and thermodynamics, are actually linked, and that actually both of them can be solved at the same time if we simply use the standard entropy definition in quantum mechanics, von Neumann entropy, and we reject the idea that the wave function is collapsing, just following the advice here of Simon Saunders. And finally, if we consider all parts of reality, not just the piece we're looking at in the environment, but also ourselves, our consciousness, as part of the physical reality, which I think was also in the spirit of what Simon said. And you attributed this, you called it whose principle? The idea that we should build in even observation and such into the Galileo's principle, yeah. So in other words, what I'm saying is that several of these pesky problems actually have the same solution, and that's the basic theme of the talk today. And the key part of the solution I'm proposing, which tends to be overlooked a lot, is the subject. Okay? So the basic idea here, which we're going to keep coming back to, is we have this big universe made of a lot of particles, or degrees of freedom if you want to be more abstract. And in the beginning, in the birth of quantum mechanics, people tended to focus only on the object, the hydrogen atom of interest or whatnot. Eventually, it became clear that actually we really need to pay attention also to the environment. This is what gave rise to the whole idea of decoherence. Feynman famously wrote that it's convenient to divide our universe into two parts. The thing we're interested in, the object, and the environment, the rest. What I'm saying is actually, don't forget this part too. And what I'm going to be saying is that when you put all three of these things together, you get a very nice, consistent explanation of all these annoying and pesky things. I mentioned yesterday, just for truth in advertising, my own views on this. I don't believe that there's any sort of secret sauce involved in consciousness. I think I am my particles. And I think it's the fact that we often have such a hard time imagining that something as prosaic as a bunch of quarks and electrons can give rise to something as amazing as your minds. I think that's just lack of imagination, actually, on our part. May and I were discussing the other day as we were looking out the window at this rabbit. It was a very, very cute baby rabbit, and Maya pointed out that, it's actually just made of clover and grass, rearranged in a different way. And if you'd never seen a rabbit, it would be pretty remarkable. You would have to have a very vivid imagination to imagine that you can just take this green stuff and rearrange it into something so amazing, right? So I think it's actually kind of a little bit arrogant of us to say that, our minds are so amazing that they can't possibly be due to some super complicated interaction of atoms. So this is my starting point. We are atoms, and that means that even if we don't understand exactly how consciousness works, we can still apply quantum mechanics even to our brains. And you can take the entire Schrödinger equation and you can decompose it. You can not only decompose the stuff in our universe into three parts, but you can also take the Schrödinger equation itself and the Hamiltonian, and you can split it into different pieces. Into internal dynamics of the object, internal dynamics of the environment, internal dynamics of our mind, and then interactions between the three different pieces. And whenever the object interacts with its environment, that's decoherence. Whenever the object interacts with us, that's observation. And as I mentioned briefly yesterday, our brains, also our neurons, certainly interact all the time with an internal environment, which causes decoherence in there, even if we've tried very hard to prevent things outside from decohering. So the information flow within these parts and the information flow between them is crucial. Fundamentally, my guess is that consciousness is basically the way information feels when being processed in certain complicated ways. Here. And then observation is information being transferred into the system from what we're looking at. And decoherence is when information is transferred from the system into other stuff. So, that's just the basic roadmap of where we're heading. Now, what are these problems that people are fussing so much about? Well, we've spoken extensively here at this meeting about the quantum interpretation problems, so I'm not going to dwell more about formulating those problems. But let me say a little bit about the thermodynamics problems. What's the fuss about entropy? Well, how did things all begin? Yeah, great old question. Well, we've made a lot of progress there. We still don't know how it really began, or if there even was exactly a beginning, but we have a very good idea of what happened during the 13.8 billion years since then, because of all the breakthroughs in cosmology which have happened. And we can see much of this now with our telescopes, and we can infer much of what happened during the first 400,000 years also from the clock data and fossil evidence left over and from Big Bang nucleosynthesis and so on. Now, what's the problem with this? Well, we find that we live in a universe where there seems to be a direction of time, right? I remember once I was working when I was 17, selling eggs on the market square in Stockholm where I lived, and I once dropped 25 eggs. It was one of the more humiliating memories of my childhood. And I sat there, and the egg was just flowing down the sidewalk. But I looked up, and the crowd had formed around me, and an old lady said, "Oh, imagine how many chickens that could have been." And then the whole crowd started roaring with laughter, and I thought, damn, why is it so hard to see through the sidewalk? And what does that have to do with this? Well, the eggs fell down, they broke, but we don't ever experience them just sort of unfalling and unbreaking again. This is a very old observation, and yet when we look at the micro world, you could actually play the movie backward of all these molecules bouncing around against each other, and it would look perfectly reasonable. So why is it that macroscopic time seems to have an arrow, and microscopic doesn't? Well, people have argued about it for 100 years. There's one very deep insight, which everybody now agrees on, which is sort of shocking, which is that the asymmetry that we see in a dropped egg in the kitchen or in Stockholm actually has its ultimate explanation in the origin of our universe. What does an egg have to do with the universe? Well, the basic answer, this dates back to early thinking even by Boltzmann and others, is of course that the reason that things are gradually getting messier and messier, and so-called entropy is rising, is because entropy was lower yesterday, was at an unusually low state yesterday, and it tends to get higher. Why was the entropy so low yesterday? Well, because it was even lower the day before yesterday. Oops, and why was that? Well, because it was even lower 1 billion years ago, and even lower at the very early stages of our universe. So you've sort of you've kicked the bucket back. It's kind of always blatant, pushing it back to something else. It's kind of like the way we try to deal with the Euro crisis. And then some people say, okay, let the cosmologists worry about that, but then there are cosmologists like Sean Carroll and others. Roger Penrose has pointed out that, well, maybe even inflation, which was supposed to create this special low entropy state, actually doesn't really solve that problem satisfactorily either. And hence the debate rages on, okay? So that's the statement of this problem. Why is our entropy so low? Our entropy could be 10 to the 120 bits or so in our universe. It's actually about 10 to the 89. It's way lower than it could be. We're not anywhere near heat death here. We're living on a 300 Kelvin planet irradiated by 6,000 Kelvin sun, cooling off into a 3 Kelvin space. So that's all we can have the complex, right? How do we understand that ultimately? So let's take a step back and just to make sure we have remind ourselves of the key tools. What is entropy? In classical physics, entropy is just a measure of our ignorance, as formalized by Shannon, who just said if you have a probability, if you have something you're ignorant of, like whether this upside-down playing card is this one or one of 8 different possibilities that you're indifferent between. So we'd say there's a probability of 1/8 for each. The entropy is 3 bits, given by that little formula. So you need 3 bits of information to specify a number between 0 and 7. If you now happen to find out that actually it's a queen, then the entropy goes down to 2 bits. You have less ignorance. If you now find out that it's a black card, you learned 1 more bit of information about the system. Entropy is only 1 bit. 0, 1, or whatever. And if you turn the card over, no more ignorance, entropy is 0 bits. Okay, that's the old method. That's classical mechanics. How do you do entropy in quantum mechanics? Well, John von Neumann provided a very elegant generalization of this to quantum mechanics, which is completely standard. In quantum mechanics, we don't have probability distributions, of course. The state of everything might be given by a wave function, as Simon Saunders said. That is, already Erwin Schrödinger pointed out in an early paper, a subsystem of something doesn't have a wave function because it's entangled with the rest. But you can always describe all there is to know about any subsystem by a slightly more general thing called a density matrix. So instead of a vector of complex numbers, it's a table of complex numbers, or a matrix, as we say in math jargon. The simplest case would be a 2x2 matrix, a 2x2 table of numbers, where if it's like this, with say 1/2, 1/2 on the diagonal of the matrix here and 0 elsewhere, we can interpret this as it's either this way or that way. Say this pen is either here or there. Whereas if you have these numbers off the diagonal, that means it's not classical uncertainty. It's actually there and there at the same time in quantum superposition. So these numbers off to the side here, if you can get rid of them somehow, you turn the and into or, and you make the classical thing, the quantum thing, seem more like a classical thing. And decoherence principle, come back to, does exactly that for you. Von Neumann's definition of the entropy says you take this matrix and you take the log of the matrix, multiply by itself, and minus the choice. And what that means in plain English is you diagonalize the matrix and then you treat the things on the diagonal as probabilities and use Shannon's formula on that. Okay? So to summarize, quantum mechanics, you just replace the probability distribution of classical physics with a density matrix. You replace Shannon's entropy with von Neumann's formula. And you're good to go. Okay? Now, so is there really an entropy problem? And why is our entropy so low? Well, philosophers are very annoying to us physicists. And I think that's awesome, because they are annoying by catching us whenever we use sloppy language and saying we need to really be rigorous. A lot of people who complain about the entropy problem, they make a terrible mistake and talk about the entropy without saying what entropy they mean. Okay, and as I'm going to explain to you shortly, that's a cardinal sin, because there is no such thing as the entropy, as I'm going to come back to. I'm going to try to persuade you shortly here that you actually each have your own personal density matrix, which describes everything there is that you in particular know about our world, and it's different, a little bit different for each one of us. And that's not in any way a denial that there also is an external physical reality. We still have a wave function of everything. It's out there. That it's very convenient that you don't need to know it to calculate everything you ever can calculate. And I'll come back to this. Now, a brief summary of where I'm going with this is my explanation of why the entropy is so low is it has two parts to it. First of all, I'm going to argue that basically the entropy of something decreases when you look at it. You get information about it, you learn about it. And it increases when you don't look at it. When it undergoes decoherence, or if you put some stuff in a certain place, if I do, and then my son Alexander messes with it when I'm not looking at it, now I know less about it. I suddenly can't find it. And that's the first part, but that's not enough, as it's going to turn out, to explain why our universe has so low entropy. So to lower entropy a lot, I'm going to show you a result that I got in a recent paper, which I'm very excited about, but when you connect this with inflation, you can get fantastic reductions in entropy and actually make a nice low entropy universe like we live in. Right? There's been a lot of nice work on the second law of thermodynamics over the last 100 years. Seth Lloyd, for example, in his PhD thesis in 1988, showed that if you have a completely isolated system where, according to standard quantum mechanics, the density matrix, its entropy never changes at all. If you just have the object doing its thing, you're not observing it, it's not decohering, its entropy always stays the same. Seth showed that if you don't know exactly what's happening to it, you can derive something like the second law. So he is in a camp who would say that the entropy is a measure of our ignorance, but that's also super controversial, okay? For example, David Albert, famous philosopher of science, who many of you know, said at a meeting that I co-organized 2 years ago that thinking that entropy has anything to do with what we know about our system is a bad, misleading mistake. Yeah, that's what he thinks. On the other hand, now I disagree, and this is actually a disagreement that goes back to an argument between Boltzmann and Gibbs about a century ago. I'm interested in using physics to figure out, to make predictions about my future, okay? And in fact, knowing the full quantum state of all of reality is neither necessary for that, nor is it in fact sufficient. Why is it not sufficient? Well, suppose I want to predict what's going to happen to me tomorrow. Okay? If I know the state of the entire universe out there, everything out there, okay? Suppose it's an infinite space, and there are several different people in there who look exactly like me and have exactly the same experiences as me. Then with this omniscient view, I don't actually know which one is this one. So I can't figure out what's going to happen tomorrow. I know this particular Max tomorrow is going to get hit by a bus because he forgot that you drive on the left side of the street in London, whatever, and this guy is going to have something better happen to him. So this indexical information about what I am is actually crucial. On the other hand, so I need to know where I am in the three-dimensional space. I also need to know where I am in Hilbert space, because if Simon Saunders is right, and the Everett interpretation is correct, I exist in many different branches of the wave function. Okay, in one I got invited to this meeting, and in another one I didn't. So if I know the full wave function, and I want to know what's going to be the first question after this talk, I need to know what branch I'm in. Okay, that's not something which it doesn't say anywhere in the full wave function because it has both. So I need to know, I need to condition on what I actually know about my location, both in 3D space and in Hilbert space, to get the right density matrix to work with. On the other hand, it also isn't necessary for me to know the state of everything to predict what's going to happen tomorrow. For example, I can safely ignore everything about the Andromeda Galaxy for tomorrow, because what's happening there right now is going to take 3 million years to have an influence on Earth, right? All that's relevant is stuff that's nearby, and I can do the operation known as partial tracing to just get rid of all that irrelevant information. That's why, in fact, we can, with our small brains, do so much useful physics, because we don't need all the information about the world to make predictions about it. That's why we can make predictions for things which are much bigger than us. Okay? So we all have our personal density matrix, which is related to the full quantum state by doing two separate things. You do conditioning, like the classical Bayes theorem, folding in the information you already know, and then you also marginalized in classical physics, or partial traits, as we call it, quantum geek speak, over the stuff that you don't need to know. Okay? So the true picture, the way to think about our universe in the ever-read picture is that really we start out in some weird quantum fuzz, the particles are in a superposition of different places, and then you evolve into a superposition of many different classical universes. We're in this one maybe where the galaxies are organized the way we actually photograph them with a Sloan Digital Sky Survey, but there's another branch where the galaxies are in a different order, where the Big Dipper has a different pattern to it, whatever. And talking about the entropy of the whole thing is completely irrelevant for us. The entropy of the full quantum state could be zero if it's a pure state. What matters is, if you know that you're on this particular branch, and you then what? And you partial trace over things you don't care about, then what's the entropy? That's what we actually measure for when we talk about that. So we should avoid loose talk about the quantum density matrix or the entropy. Alright? So what can we do about this then? Having said that, there are some very specific mathematical recipes. There are 3 cookbook recipes for dealing with all of physics. Cookbook recipe 1 is what we all learn in kindergarten or grad school or whatever when we first took quantum mechanics. If the object is not interacting, it's just interacting with itself. Then we use unitary evolution, we solve the Schrödinger equation, and figure out what's going to happen. Okay? For example, as we saw yesterday, if you put an object like a card balanced exactly like this, it'll fall down in the superposition of 2 different places. It's an example of where entropy does not change. Start with being in a definite quantum state. Now you're in a quantum state too, albeit the sort of Schrödinger cat-like one. The second interesting case is when the object interacts with the environment. Causing the environment to learn information about what the object is doing. And it was famously shown first by Dietrich Say and then pioneered by a lot of nice work, Wojciech Zurek and many others. What that does is it takes this density matrix and exactly gets rid of these off-diagonal elements, basically changing and into or. Now it's here and there, and now it's here or there. Effectively, in 2 places at once. We can think of things as having branched, as Simon said, even though, of course, there's still just one wave function. Okay, that's what the appearance does. I'm not going to bore you with all the math here, so you should read about that elsewhere if you want to. But the bottom line is, with only 1 page of math, you can derive this very simple result. It's the magic off-diagonal numbers which still distinguish between quantum superpositions and just classical ignorance that made to go away. The key thing about this is it doesn't say anything about what kind of system it was that involved in this math that interacted with the object. I, in this calculation, used the simple smiley face and sad face for the system that was kind of observing the object to sort of make you think that it's a person looking. But the math doesn't care. You can use whatever symbol you want. So this leads to the very, very simple answer to the question of what counts as an observer, actually. Do you need to be a human or a mouse or a robot, or does it suffice with a photon? Einstein wondered about whether a mouse looking at the moon would actually, affect it. We now have a very simple answer to it, which is all of the above will count as having these effects. What matters isn't whether you're conscious or not. What matters is just the transfer of information. If you have something which is both here and here at the same time, for decoherence to take place, it'll work just fine if for example, Simon Saunders comes out and looks at it and then walks away. But it'll work equally well if just one particle of light comes in and bounces off of it. Bounces away, because now where that particle of light is going to be a little bit later will depend on where it was, right? So by looking at where the photon is, you can figure out where the remote control was. The information has leaked out. You can think of it in a way, keeping quantum mechanical being all about keeping things secret. As soon as the information about what's going on leaks out, anywhere else, whether it be encoded in a human brain or in the position of a photon, you're no longer going to be able to measure any interesting quantum behavior there. Alright? Let me to say a couple of other quick things about decoherence also, because I want to just make clear this is not just something very philosophical, it's something very practical you can calculate all sorts of things with. First of all, decoherence is actually the fastest process in nature by a huge amount, okay? And just to appreciate that a little bit, suppose I take a cup of coffee from outside and I drop a sugar cube into it. And I think that my sugar cube is system one, the object, and the coffee is the environment. There are going to be several, this is going to interact with the coffee as it hits it, right? There are going to be several things happening. There's going to be some dissipation, where some of the energy of the sugar gets dumped into the coffee. It's going to slow down through friction. There'll be some fluctuation also, Brownian motion. If you look really carefully on the sugar from the random motions of the molecules in the coffee. There'll also be communication, whereby information is transferred. So there'll be information in the coffee about exactly where the sugar fell from the waves in the coffee, right? And as a result of the information transfer, there will be decoherence. And for each of these four kinds of processes, you can write down a time scale. How long time typically does it take for this thing to be important? Because the dissipation time scale is the time it takes for about half the energy, say, of the sugar of motion to be lost, right? And that scales roughly like the number of particles. If you have 10 to the 25 particles in the sugar, they each have energy, and you have to have about 10 to the 24, 10 to 25 collisions until with coffee molecules or water molecules until you've gotten rid of all the energy. But how long does it take for information transfer to happen? It takes only one collision. The first collision that happens between any of the 10 to 25 sugar molecules and one molecule from the coffee cup already gives away all the whole secret about, oh, it's here. And what that means is that the process of decoherence is about 10 to the 25 times faster than the process of dissipation. It's huge. That's why it's a ridiculously fast effect, because dissipation and fluctuation is about the transfer of information. Sorry, transfer of energy, to slow. Decoherence is about the transfer systems by what the ratio is of the dissipation to the decoherence time and the dynamical time of motion compared to decoherence. It separates that very nicely. So you see things are going to act it'll act quantum if both the decoherence time is very long and also the dissipation time is very long. So they're acting kind of independently and they don't decohere. If they decohere, but they're still dissipation and friction still it's slow enough to leave them a lot of autonomy, that's classical systems. But if the dissipation time also is faster than the dynamics time, that's like if you have a little pebble that you've thrown into a jar of honey. Dissipation is so big it doesn't really have much dynamics of its own at all, and it's not an independent system anymore. Okay? Another thing worth stressing about this is you can put numbers to all of this. In fact, the very first paper I wrote in my entire life was just working out a bunch of time scales for these things. You can take, for example, a bowling ball and ask, how often does it bump into something? Well, an electron gets bumped by air molecules here in this room every 10 to minus 13 seconds. It doesn't get bumped very often at all by a solar neutrino. You can put numbers to all of this stuff. And the bigger the thing is, typically, the more it bumps into the environment. So we realize that the reason that big things tend to look classical isn't because they're big. It's just because big things tend to be harder to isolate from the rest. And we also know that if you take a thing that's isolated and just leave it alone, its quantum wave function tends to spread out. But every time it bumps into something, these quantum superpositions get destroyed by decoherence. So there will be sort of an equilibrium coherence length of each kind of thing. And you can see, if we put a bowling ball in this room, its coherence length is 10 to the minus 21 meters. So you can never mention any weird quantum bowling things. I have to make other excuses for bowling so badly. Okay? Whereas if you have, for example, even if you take little things like electrons, it's pretty easy to have them spread out over very, very large distances, especially if you pump out the air of your experiment and so on. But for big things, it's really hard. You can never get rid of the solar neutrinos, for example. And even if you do perfect vacuum, super low temperature, bowling ball is always going to be pretty localized, just because it gets hit by solar neutrinos, once in a while. I have to also confess something to you, Joe, which you would say never. I don't think I confessed before. This was my first paper ever, but I actually never showed it to you when I was a grad student because I was embarrassed and I thought you were going to disapprove of it. So I checked that you were far from the laser printer before I printed it out, and I didn't show it to you until after you signed my PhD thesis. And that's so ironic because now I realize that you were all along much more open-minded about these things than I gave you credit for, and you're even inviting me now to speak about this. So it brings closure to this. I'm now fully out of the closet. Let me skip over this little. This is, if you download my very last paper on the archive about the post, it's about how you can explain why space-time looks so classical using decoherence, because neutrinos and things keep flying through space. I'm going to spare you the details of that. Let's talk now instead about the third interaction, and the subject that we're interested in interacts with us, observation. That was the main topic of yesterday's lecture that I gave. So if I interact with it, then my state, it's not the environment that gets entangled with the thing, it's my mental state that does. If I bet money on that this card is going to fall down face up, then when I look and see that, I get happy. And then the other branch of the wave function, card is down, and I'm unhappy. And because of decoherence, we can think of this, as Simon said, as the universe having split off into two parts. This is a summary table of how all these three kinds of processes are linked to one another, okay? If the object interacts with itself, then this is how the density matrix evolves unitarily. Entropy stays the same. When the object interacts with the environment, you get decoherence. This is the most general formula for the most arbitrary weak interaction or strong or whatever you want with the environment. And that increases the entropy. And in a recent paper, I also worked out the most general effect on the density matrix from observation in the many worlds formalism. And this is what the formula looks like. I can give you the paper afterwards when I look into the math. And here, generating entropy decreases, just like you would expect. And this last formula here actually is exactly the quantum mechanics version of Bayes' theorem, for those of you who are familiar with this. Bayes' theorem says that if you don't know for sure what's going on, but you have a probability distribution reflecting your credence in different possibilities, then when you get more evidence, you make some kind of observation, it gives you a rule for how you should update your probability distribution to factor that in. What this formula does is exactly the same thing. You have your personal density matrix, which summarizes all your knowledge about the rest of the world. And then when you learn something by interacting with the world or the object, this formula shows you how to update your personal density matrix. And this lets us come back to this touch the third rail now and talk about the second law of thermodynamics, which is so controversial. And say a couple of more nuanced things about it. It's simply not true that if you define entropy as the von Neumann entropy, that entropy always increases. Obviously, that cannot be the case. So, if you're going to have some explanation for why it's so low now. Crudely speaking, increases when you don't look at the world, and it decreases when you make observations. So we can say that the second law of thermodynamics, part 1, which says that the entropy of the object cannot decrease unless it interacts with me, unless I observe. So the standard second law of thermodynamics is perfectly true, in other words, as long as I don't make an observation. And sure enough, already when they first formulated the second law, Maxwell's demon came along, right? And which shows a kind of violation.